Hello again. I am Patrick from Sumisol Machinery Solutions. Despite being followed proper design practices of mission-critical rotating equipment, high vibrations were experienced when installed and tested at OEM works and at site. This presentation endeavors to present few cases on the topic. In this informative video, we shall be explaining 7 failure cases where the machines behaved against the anticipated pattern due to wrong installations, operations, and testing conditions. The first case is related to machinery component vibration in pumping unit trips caused by high vibrations were reported in VSD motor with gearbox driven in all QANATPLEX plunger pumps at site during startup and operating regime, 70 to 80% of full RPM. The pump maximum operating frequency was 16 Hz. Actions. Several attempts were made to undertake all possible corrective actions, such as checking levels and correcting the positions of shims with no favorable results. A third-party vibration survey with a run-up and run-down measurement distinctly indicated that the motor experienced resonance at 70 to 80% of rated RPM. During design phase, FE model showed there is an adequate separation margin between skid natural frequency and complete operating frequency regime. However, based on bump test and run-up and coast-down vibration data, it was found that skid natural frequency is in close proximity with 80% of operating frequency. The FE model was revised based on the ODS value of 12 to 13 Hz in motor pitching mode, and this was found as weakness in individual structural members. There were 2 options suggested by expert team. 1. Strengthen the identified structural members. 2. Restrict the movement of structural members by pouring grouting, which in turn can raise the stiffness and then the structural natural frequency. In both ways, adequate separatio margin can be achieved. However, after deliberations and understanding the complexity of working on option 1, it was decided to undertake monolithic grouting of skid with existing foundation. Revised FE modeling with monolithic grouting with existing foundation revealed a high separation margin from complete operating frequency regime. Hence, the proposed solution provided a high amount of confidence. To ensure a monolithic structure of the existing foundation and no shrink grout filling, rods were inserted between base plate and foundation to recreate a rebar-type structure and unified foundation. An elaborate method used to meet the purpose, such as drilled 5 large diameter holes in the skid top plate to allow for cement grout pump hose access. 5 rebar placed in the drilled holes through the cement grout have several functions. Main one is to act as a shear pin between skid fill and foundation. The number of rebars, 5, used was the same as the number of access holes drilled. Use of breather holes to access areas that require additional injection work. The unit was supplied with VFD-driven motor to supply flow on demand. However, due to logistic issues, the VFD-driven motor was not used. Instead, a flow control valve was used to vary suction flow conditions generated by variable speed pumping. Hence, the possible resonant condition at particular speed band could not be captured. The second case is related to high-voltage electric drive. During installation of a heavy-duty electric, cracks were found at 2 different places of end shield. To meet the installation and commissioning schedule, the shields were replaced by locally fabricated shields but with little reduced thickness. During commissioning, the velocity transducer installed on the non-drive/exciter end of the generator measured high 2xn vibration in the axial direction at a frequency close to the equipment operating frequency. The levels exceeded the IEC 60034 to 14 grade B acceptance criteria of 1.5 mm per second RMS for solo run test. The first natural frequency of end shield was found as around 120 Hz, 120–124 Hz, which was in resonance with 2 FL excitation force from motor. From those reason, the axial vibration level on bearing housing reached to the 7.5 mm per second RMS. By adding mass as horizontal bar, overall first natural frequency came down to 112 Hz. Another simulation was done to remove mass, creating holes to reach 110 Hz. However, addition of stiffener was considered in execution as step-gap arrangement till the new end shield was dispatched at site. The stiffness of a motor's components, rotor, stator frame, shields, is crucial for structural integrity and dynamic response, and the presence of cracks significantly reduces this stiffness. This fact was overlooked and immediate corrective action was not taken. The third case is related to centrifugal compressor transient vibration. after 8 hours of pressurized shutdown, centrifugal compressor could not pass first bending critical speed during startup. Compressor tripped on high shaft vibration. The rotor had passed the MRT, string test, and at site 96 hours endurance test. Startup engineer and operations started thinking about implemented a soft start. Exercising UNISC, a trip multiplier, was considered but was not agreed by OEM. Further analysis and comparisons of startup Bode plots were carried out. Looking at Bode plot, amplitude appears consistent, phase is highly irregular. An APHT plot was used to identify such phenomena, which revealed a possible thermal bow in compressor rotor. To find the credibility of possible thermal transient bow, causal effect were studied and was revealed that high-temperature external seal gas at 130 degrees centigrade created localized heating of rotor. For the purpose of removing sulfur from external source, the gas is heated to 130 degrees centigrade to avoid deposit of sulfur in dry gas seal cavity. To avoid such trips during startup, facility for circumferential seal gas distribution in seal was incorporated. As an ad hoc basis, trip multiplier was introduced during startup. The fourth case is related to catastrophic rub in centrifugal compressor. The subject centrifugal compressor was single-shaft multistage centrifugal compressor between bearing design with back-to-back impeller configuration as shown in figure. With proper test bed set up, centrifugal compressor was being tested, and after 4 hours run, while coasting down, compressor tripped on high vibration. On monitoring panel, seal gas high flow alarm also popped up while machine tripped at high vibration. Upon investigation of plots and subsequent inspection, it was found that rotor suffered a rub-related damage. After detailed investigation, it was found that OEM procedure was to use partly vacuum media, and buffer media used for dry gas seals was air. It is known that at 70% of seal air goes to process stage based on differential pressure. Hence, air being at higher pressure than part vacuum could easily ingress into the clearance between labyrinth and impeller eye and caused a windage effect. Local windage can cause high local heating. This leads to thermal expansion of impeller hub and labyrinth, and they tend to come closer. In vacuum, heat dissipation is quite less by convection. Air is bad conductor of heat. It was later proposed to have either proper extraction of hot air or use gas mixture which have lower polytropic exponent. The fifth case is related to disc ACK coupling. During first run of compressor train at manufacturer's facility, high vibration affected the gas turbine and the gearbox. Connected by the low-speed coupling, during the investigation we discovered some small chips inside the coupling. The coupling was replaced by the spare one, and vibration of gas turbine and gearbox low-speed shaft decreased within the acceptable value. Later on, while dismantling, canning effect was found in disc pack. This was due to continuous operating in wrongly assembled coupling. Canning is the term we give when the element pack no longer has a natural center. It should return and sit parallel to the flange faces. One side of the pack is elongated while the other is compressed. Moving the spacer does not correct the condition but simply reverses the pack. The condition is usually caused by overcompression, though other factors can also attribute. Severe overcompression of the elements can exceed the friction holding the blades together. Loosening and retightening the coupling bolts usually corrects the problem. To strip and reassemble a coupling and have the amount of balance only double is very good and is testimony to its good machining accuracy. Sixth case is related to coupling-induced vibration during the MRT in compressor manufacturer test bed. High vibrations were detected at the driven end probe location. These vibrations were of such an extent that the MRT was cancelled and an investigation was started to determine the source of the vibrations. Closer examination data showed as speed was increased, the vibration first increases exponentially, then stabilizes, and after that slowly decreases again. Simultaneously with the increase in vibration, a change in phase can also be seen. 1x filtered orbit plots at DE and NDE compared, which showed a greater amplitude. The orbit plots were found to be perfectly shaped, indicating no rubbing takes place. It was noted that during the test a shop coupling was being used instead of the specific job coupling. Comparison between test coupling and job coupling is shown in picture at right side. Overhung weight of test coupling is significantly larger than that of the job coupling. The rotor dynamic check showed that the rotor with shop coupling mounted is likely to become thermally unstable. The rotor with the intended job coupling mounted is calculated to be thermally stable. Test was conducted with contract, job, coupling after few weeks and vibrations were much below API acceptance criteria. The seventh and last case of this presentation video is related to medium-duty generator bearing. Bearing shell was found with complete lacking of oil, the shell was dry, and steel dust. The white metal was completely worn out and also the steel was partially scratched. The fault caused the NDE sleeve bearing causing high vibration and after inspection the failure was observed. This failure was due to low oil level, while no further damage was found in other parts of alternator as DE bearing, windings. It was concluded that the problem of low oil level was overlooked since all the tests were carried out at the factory with auxiliary power present, therefore lubrication pump was always running on previous occasions. Sumitech Turbomachinery Solutions constantly endeavors to support machinery failure prevention. We shall be sharing more knowledge-sharing videos and technical write-ups. Contact us at sumitexel17@gmail.com for further tailored support.